All right, so here we go. So we're going to learn today about conservation of angular momentum. And there's really kind of three scenarios, I guess, that you need to be familiar with on these, all right? So I'll run through three examples. This one's going to be probably a little bit on the long side, so apologies in advance. All right, here we go. So let's begin. Here we go. So conservation of angular momentum. So when we studied linear motion, we learned that in a closed system, in other words, if there are no external forces affecting the system, the total momentum remains constant. In equation form, we did a lot of this. Total momentum before the collision equals total momentum after the collision. And then remember, that was just this. It was the mass of particle A times the velocity of particle A initially, plus the mass of particle B times the velocity of particle B initially, equals the mass of particle A times the velocity of particle A final, plus the mass of particle B times the velocity of particle B final, right? And it's just kind of plug and chug. All right, so this chapter is basically going to be the same thing. The difference is this time we're going to be talking about angular momentum, all right? And so it turns out if there are no external torques, then by the exact same logic, it turns out that your total angular momentum is going to be constant. And so our new equation becomes this. The total momentum before some interaction occurs is equal to the total momentum after that same interaction occurs. Okay? So let's run through an example here. All right? So on our playground, wait, you can read through this. So pause it, read it. Cool, done. All right, so let's take a minute and write out what we know. So here's what we know. So for Sally, I know that the mass, I'm going to use a little m for Sally and a capital M for the merry-go-round, okay? So I'll try to make sure I make those clear. All right, so the mass of Sally is 40 kilograms. The velocity of Sally at the start is 3 meters per second. All right, and then over here we've got this merry-go-round. All right, the merry-go-round has a radius. I'm going to use a capital R for that radius. I guess it doesn't matter, the radius. No, that's not ice cream. Okay, so the radius for the merry-go-round is 1.2 meters. Oops, more M's. Meters. And then the mass of the merry-go-round is 160 kilograms. Now, the problem tells us that at the beginning it's spinning with a period of 8 seconds. So the reason we need that is so we can find the angular velocity that it has at the beginning. So remember, that's just 2 pi radians in 8 seconds, right? Right? Because the period is the time to go around once, 2 pi radians. All right, so if you divide that, you get 0.785 radians per second. Now, the other thing is if you read it carefully, it tells us that it's initially spinning towards Sally. All right, so let's make a top view of this thing. All right, so here's Sally. She's got a mass of 40 kilograms. She's moving this way at 3 meters a second. And she's going to jump onto this merry-go-round, which is spinning towards Sally. All right, and we want to ensure that when we consider our linear and angular velocities, we want the linear velocity of a point on this thing to have the opposite sign as Sally's. Okay, so I'm going to make this initial angular velocity negative to indicate the fact that it's going, the linear velocity is going to be in the opposite direction as Sally's. Okay, so notice we usually do counterclockwise as positive. Here I'm kind of breaking that rule, right? So remember, those signs are arbitrary, and so you need to make sure that your signs, the way you set up your signs for your problem, agree with each other. Okay? Okay, so that's our starting point. All right, so let's smoosh some of this down so that we have a little bit more room to work. So question A says, what is the initial angular momentum of the merry-go-round about its axis of rotation? So question A, what is the angular momentum of the merry-go-round initially? All right, well, that's just the rotational inertia of the merry-go-round times the angular velocity of the merry-go-round initially. All right, so let's see, rotational inertia of the merry-go-round. Well, it is a disk, so that's 1/2 times the mass of the merry-go-round times r squared times the initial angular velocity of the merry-go-round. So what are we going to get? Let's see, 1/2. Mass is 160 kilograms. Radius is 1.2 meters. Don't forget to square it. Times our initial angular velocity, which is negative 0.785 radians per second. So multiply that all out, and you get negative 90.5 kilogram meters squared per second. Okay. The next thing we need to do is part B, which wants the initial angular momentum of just Sally, right? So here we go. Question B, the angular momentum of Sally initially, excuse me, that was gross, is, well, look, she's a point particle, right? Traveling about this pivot point, right? So it's going to be mvr. We've got our mass, we've got our velocity, and then the radius, remember, you measure perpendicular to the motion. So it's just the radius of the merry-go-round, okay? So mass of Sally is 40 kilograms. Velocity of Sally is 3 meters a second times the radius, 1.2 meters. Multiply this all out, and you get 144 kilogram meters a second, all right? So those are the angular momenta, if you want to be specific. Those are the angular momenta of the two objects before the interaction occurs, right? Now, what's going to happen is she jumps onto the merry-go-round, all right, and she sort of like sticks to it, right? Because once she's on the merry-go-round, she and the merry-go-round are going to be spinning together, okay? So B wants to know what is her speed after she jumps onto the merry-go-round, okay? So let's do this. Let's go 2 pages here. All right, so our total angular momentum before she hits the merry-go-round is equal to the total angular momentum after she hits the merry-go-round. So total angular momentum before she hits the merry-go-round is the negative 90.5 from the merry-go-round, kilogram meters squared per second, plus 144 kilogram meters squared per second. That's got to equal, well, let's see, it's equal to the angular momentum of the merry-go-round after plus the angular momentum of Sally after, right? So the left-hand side of that equation is this. Angular momentum of the merry-go-round, well, that's I times omega. Well, I is just this again, right? So 1/2 times 160 times 1.2 squared. There's the angular momentum of the merry-go-round times its final angular velocity. Plus, now this is a little bit weird. Because they're stuck together, both the merry-go-round and Sally are going to have the same angular velocity. Okay? So when I did this over here, I treated her as a point particle, right? But when you do that, you're considering the linear velocity of the point particle. And we don't want to do that because we need our equation over here to have angular velocity. So I'm going to now treat her as a point particle rotating. So her angular momentum, remember, angular momentum of a point particle is mr squared. So I'm just going to do I omega. So I for her is her mass times the radius squared, right? That's her rotational inertia, mr squared for a particle, times her final angular velocity, okay? All right, so this mess, when you solve it, gives 53.5 kilogram meters squared per second. And that equals this mess, when we combine our like terms here and here, you end up getting 172.8 times omega f. And so when you solve, her final angular velocity is 0.31 radians per second. But the problem actually wants her speed. And so her final velocity then is omega times r, right? So 0.31 radians per second times the radius, which is 1.2 meters. And so she gets a velocity of 0.372 meters per second. All right? So that's one of the 3 scenarios. You've got a collision between 2 objects that have angular momentum, right? And in this case, it happens to be, what would it be, perfectly inelastic, right? Because Sally sort of sticks to the merry-go-round. That won't always be the case. It very frequently is, but not always. Okay? Cool. So notice here there are no external torques, right? The only 2 torques are Sally applying a torque to the merry-go-round and the merry-go-round applying a torque to Sally, kind of. And so there's no change in angular momentum, which is why we were able to do this. All right. Now, in part D, Sally's going to crawl to the center of the merry-go-round. Okay. So, again, Sally's going to push the merry-go-round is going to push her. No external torques, so our angular momentum is going to be the same. Here's the only difference, is that we're still going to have the same total angular momentum, but once she's done crawl, let's see, that doesn't change the merry-go-round, right? But as she crawls to the middle, so originally, here's the merry-go-round, here's Sally. She's at a radius of 1.2 meters, right? And she's going to then crawl in towards the center. And so her radius will be 0.6 meters.
What, Mr. Becker?
What are you doing, Mr. Hernandez? And so that's just going to change the radius here to 0.6 meters. All right. So when you go through and do the math, you know, it's literally just this exact same thing we did, except you're changing the 1.2 to 0.6. What we discover is the merry-go-round is now spinning with a faster final angular velocity of 0.41 radians per second. It's spinning faster, right? Okay, now linear velocity ends up being smaller. So if you do, let's see, her angular velocity, it's her radius, right, because now she's 0.6 meters away, it ends up giving you 0.25 meters a second. So she's got a smaller linear velocity, but a bigger angular one. Okay, and the reason there is when she moves in towards the center, it decreases her rotational inertia, and since the angular momentum has to stay the same, she spins faster. In English, angular momentum. So at the beginning, she's far out, and so that gives her a large rotational inertia and a small angular velocity, right? As she crawls into the center, our radius gets smaller, and so our inertia gets smaller, and as a result, we have a larger angular velocity. All right, it's the exact same thing as a figure skater pulling her arms in, or his arms in, and spinning faster, right? So let me show you, all right? So here we go. So these two bricks represent Sally, okay? I'm gonna be the merry-go-round, okay? So right now her mass is far out, right? Oops, she's spinning, oh shoot, failed. Try again. Okay, so right now she's spinning slowly. When she crawls into the middle, she spins faster, right? Notice the velocity of the bricks is small because there's zero radius, but there's definitely a higher angular velocity, right? So here it is again. So spinning, crawls into the middle, spins faster, or slower, or faster, or slower, or faster, right? Cool? I am really dizzy. All right. Ah! All right. Cool. So that's that. So those are two of the types of examples. Example number one, you've got these two objects sort of colliding with each other, and the momentum is conserved. Example number two, the mass gets repositioned, but your angular momentum is still conserved. All right? So then the third example is actually another collision, but we also need to consider conservation of energy. Okay? I am still dizzy. So let's see if we can get through this. All right? So we're going to go back to that meter stick that we had in the last example, all right? It's going to be suspended from one end, and then we've got a glob of clay that's going to get fired at it, okay? So it's, you know, it's this thing. Here's our meter stick. Glob of clay is going to get fired, sticks to the meter stick and causes it to swing, all right? And we're trying to figure out what angle the meter stick will make with the vertical when it stops and swings back down, all right? So there are actually three parts to this, all right? So there's there's 3 points. We'll call them point one, which is the clay. Let's see, what do we know? The mass of the clay. I don't want to do this. Sorry, I'm being silly here. All right, let's just make drawings of the three positions. So here's the clay and the meter stick, right? So that's point number one. The clay is moving towards the meter stick, which is hanging about this pivot point. Part two is immediately after the collision. Now that whole thing is going to be rotating, right? Because the clay is stuck to the meter stick, and so the meter stick is going to be swinging. And then part 3, the meter stick is going to swing up to some height. Oh, shoot, I goofed. The meter stick, or the clay is not hitting the end of the stick. I'm going to make my meter stick a little bit longer. Sorry. Okay. So, and so then this is the point where the meter stick stops swinging and it's going to swing back down. Okay? So the idea is between here and here, we've got a collision. Oops, that is not at all how you spell the word collision. So between here and here, we've got a collision. So you should be thinking, oh, conservation of momentum. In this case, conservation of angular momentum. And then between here and here, the collision has already occurred, but we're simply converting the rotational kinetic energy that the disk or the meter stick has after the collision to gravitational potential energy afterwards. So this is a conservation of total energy problem. Okay? So we've done stuff like this before, but just not from the perspective of angular momentum, just from linear. Okay? All right, so let's do this. So here's what we know. We know that the angular momentum in drawing number 1 is equal, the total angular momentum is equal to the total angular momentum in drawing number 2. So let's see, for the clay, we know that the mass is 0.05 kilograms. We know that the initial velocity is 4 meters a second. And then we know that the radius for that chunk of clay is 0.50 meters. All right? And then for the meter stick, we know that the mass, capital M, is 0.09 kilograms. It has a radius, big R, of 1 meter because it's a meter stick. I know that my rotational inertia is 1/3 mr squared, which when you solve that, it gives you 0.03 kilogram meters squared. And I know it starts at rest. All right, so. Stupid smartboard. All right, well, it's not going to cooperate, so we're just going to have to, all right. Okay, whatever. All right, so here we go. So angular momentum initial equals angular momentum final. So that means the angular momentum of the clay in drawing number 1 plus the angular momentum of the meter stick in drawing number 1 has to equal the angular momentum of the clay in drawing 2 plus the angular momentum of the meter stick in drawing number 2. So let's see. This is mass of the clay, velocity of the clay, radius of the clay, plus inertia of the meter stick, angular velocity of the meter stick, right? Equals, on the other side, well, on the other side, I'm going to want to consider the angular velocity of the meter stick in the clay, right? Because that's my unknown, right? I don't know what the angular velocity in this middle drawing is. So I'm going to do rotational inertia of the clay times angular velocity of the clay plus rotational inertia of the meter stick times angular velocity of the meter stick. But since they're stuck together, they're equal. So I really don't even need to distinguish between my 2 angular velocities, right? Because this and this are the same, which is the whole point. Okay, so let's plug in our numbers. You got 0.05 for the mass times the velocity, which is 4, times the radius, which is 0.5, plus the starting momentum of the meter stick is 0. And then afterwards, let's see, rotational inertia of the clay, so that's mr squared. So 0.05 is my mass, radius is 0.5. Don't forget to square it, times omega, plus rotational inertia. Remember, we found the rotational inertia of the meter stick. It's down here at the bottom of the screen. My smartboard is not cooperating, but it was 0.03 times omega. All right, so solve this mess, and you will discover that the angular velocity of the meter stick in the clay right after the collision is 2.35 radians per second. All right, so let's write that down. 2.35 radians per second. Okay. All right, so now what we got to do is we got to go back to conservation of energy from the beginning of this unit. And so now what we're going to do is I'm going to say, oh, well, I know that the total energy in drawing number 2 is equal to the total energy in drawing number 3. So what I'm going to do is I'm going to call the height of the center of mass a height of 0. Height equals 0, okay? And so the idea is our center of mass is going to go up, right? Also, notice that because the clay is hitting the center of the meter stick, the center of mass is always the center of the meter stick, right? Because the clay is at the center of mass of the stick itself, okay? So here we go. So that means that the rotational kinetic energy in drawing number 2 is equal to the gravitational potential energy in drawing number 3. So 1/2 times, all right, my I is both I's. It's the I for the meter stick. Oh, well, we figured that out, right? That was the 0.03. So there's I for the meter stick, plus I for the gum. Remember, that's mr squared, right? So 0.05 times 0.5 squared. So there's rotational inertia times angular velocity, 2.35 radians per second squared. So this is 1/2 I times omega squared, all right? So that's got to equal the GPE in drawing 3, which is just the total mass. So let's see, the mass of the gum, or the clay rather, is 0.05. Meter stick is 0.09, so that's my mass times G times some unknown height. Okay, so solve for the height and you get 0.857 meters, except my decimal's in the wrong spot. Okay, so what that means is when it's done swinging, here's what we've got. So I know that this distance is 0.5 meters. I know that this distance is 0.5 meters. This height that we just found here is from there to there. So that's 0.0857, which means that this height is 0.414 or 413. One of my roundings is funny there, but whatever. 413 meters. Oh, darn it. That's not right. What did I do? Let me grab a calculator. Calculator. Oh, yeah, that's right. I see. 0.414. I was right the first time. 0.414. All right, so now I've got this blue triangle here. 0.414, 0.5. We want to find this angle. So our angle is, what is that? It's a right angle, right? So inverse cosine of adjacent over hypotenuse. And it gives you 34 degrees. So there you go. There's your answer. All right. But the big thing I wanted you to notice about this is there are definitely going to be problems like this. This is a fairly common thing. I've seen problems very similar to this on AP exams. But I just want to make sure then that you understand there are two parts here, right? Conservation of momentum during the collision, and then conservation of energy after the collision. All right? I believe that's it. Hooray! That's the end of chapter 13. We're killing it, you guys. All right. Have a good one.